So in another video I introduced the idea of the difference between the order of evaluation of Java's operands versus the operations themselves. And I realized that I didn't do a particularly rigorous job of explaining why these rules were these rules. I just explained what they were and how they worked. But I thought it might be a useful thing to take a look at the piece of the language spec and expand on this idea just a little bit. So here's the relevant piece, section 15.7 and 15.7.1, which says that the Java programming language guarantees that the operands of operators appear to be evaluated in a specific evaluation order, namely left to right. One thing worth pointing out is it says appear. It doesn't matter if things are done in a different order if it makes no difference to the final result and all the side effects of that set of operations. So optimizations are still possible, but you must not be able to tell what order it was executed in as being different from the required order. Of course, and I said this in the other comments about evaluation order, any code that uses this kind of dependency is by definition horrible. I think there's really no other circumstance, no other wording you can use for this. Things that have side effects in, generally not a good idea. It makes it hard to understand, seemingly magical, and hides things that normal programmers would possibly miss. So then, as we scroll down a little bit, let me come in here. You'll see that it says we evaluate the left-hand operand first. So the left-hand operand of binary operators appear to be fully evaluated before any part of the right-hand operand is evaluated. Now notice this is the evaluation of the operands themselves, not the operation. And you might reasonably be forgiven for wondering what on earth that means. But if we take a little look further down still, they actually have a simple example that tries to make this point. Here, they have a simple assignment to I of 2, and then they perform a more complex thing. This, with luck, you remember that Java's assignments have value. So when you do an assignment, whether it's a simple assignment with equals or a compound assignment with the assignment operators like plus equals, minus equals, the thing that gets assigned, the value that gets assigned, is the value of that operation. So here the value of this is 3, as well as assigning 3 to I. But the question is, what value ends up in J? Because we have an I here, which is multiplied by this I equals 3. So what value is actually expected to be there? Because initially, of course, we have I equals 2. So if it uses I is 2 and multiplies that by 3, you'd expect it to be 6. And if it uses I is 3, then 3 3s are 9. And it says unequivocally the program produces the output 9. In other words, this left-hand side is executed and I is 3 before we multiply by whatever I contains, which is now 3. Now, I thought what I might do is to take this code and build a slightly more complex example out of it. I mean, this makes the basic point, but I equals 3, would you ever do that in the middle of things? Well, actually, yes, that's not a totally outrageous thing to do, but it's perhaps not ideal. However, what I did was I took this example and I changed it up just a little bit because one of the things where side effects can be particularly unpleasant, particularly tricky, is when we have array subscript access. And this is quite often tempting to do because we might decide that we're trying to perform, if you like, matrix arithmetic. We're trying to take the contents of an array and take this piece, multiply it by the two things on either side of it, and do something else. So we start out by allocating a very simple int array such that the values in each element are the same as the subscript, so we can see what's going on. So an array with 0, 1, 2, 3 in it. Then we have our simple int, and we initialize that with 0. So notice it is initialized. Obviously, this is a local variable, so we are responsible for that ourselves. Then our expression is going to calculate I equals 3 times I. But instead of assigning it to j like they did in the language spec example, I'm going to assign it to an element of this array. Yeah. So IA plus I equals 3 times I. I really hope it's obvious that we shouldn't be writing code like this, but nevertheless. One of the things that we might reasonably expect is that the order of these operations, clearly this is parenthesized, so that sort of has to happen first, right? Because it's there in parentheses, and we can't assign anything until we have calculated the value. So our instincts are probably that we will assign 3 to I, then multiply by I, which would make us 9. And then that we would increment I and get 10, because now we need to do the assignment to IA on the basis of that subscript. But what's actually going to happen is that we evaluate the operands in effect from left to right. So here, plus I specifically is 1. And that means that IA of plus I is actually a reference to that element of the array. Now, the things on the left-hand side of an equal sign obviously have to refer to something that can be changed. The word for that is an L value. And now that left-hand expression has evaluated as a reference to that element of the array, IA. Now we move across to the right-hand side and we evaluate this expression. Well, technically we evaluate that expression and say, where are we going to store this? Evaluate that expression and say, oh gosh, it's 3. But then we evaluate this whole expression, and that, of course, has the value 3. But so does I at this point, because now that is going to be 3. And so 3 times 3 makes 9. And we should find that when we run this, we do in fact insert 9 into our array, like that.